because we're actually just copying the keys around. So in the Quicksort, our data is, remember the list please, same list.
31, 71, 23, 73, 29, 91, 79, 53, 47, 37.
Okay, on pass 1, if we choose that as a partition element, then we put down the partition element and then we run through the list. If something is bigger than the partition element, it stays in the last part of the list. Smaller, it's up to the front part of the list. So, actually, the cursor copying may involve some amount of swapping, but I'm just going to write down the end result of the partitioning rather than going through and showing where the swappings are done.
You're supposed to show that?
Yeah, I'm showing the states of the list after each step, after each call to Quicksort. Now, while the list is being partitioned, you're going to have several stages of swapping to get everything that's smaller than this item in the front part and everything larger in the second part. But I won't show all those swaps. So, if that's a partition element, 23 is less.
Put it to the front. So we'll go to the center one first, right?
Right. And that would be, alright. Let me show them then. You then, alright. One way of doing it is to start with what I call a high pointer and a low pointer. I'm going to show the first pass of partition. After the first call to partition, then we may move a little faster. So from here, we check to see, let's call this high, or call this low, this is high. Compare that with the partition element. That's large on the partition element, it stays, and we drop the high pointer. Now we keep on reducing the high pointer until we find something that's smaller than the partition element. So that will continue until we're there. Alright, let me let the original list stay. And I'm going to rewrite the list and then make my swaps in place in that rewritten list. So, if we have 31, 71,
23, 73, 29, 91, 79, 53, 47, 37.
so the first swap we'd make is when high gets to 29. So we'd copy the 29 down here. And the 31 will be swapped with this.
Why not start with 23 first, sir? Which end are you coming from?
We're moving down the high pointer.
Okay, okay.
Then we still have our low pointer. So high is pointing to this position. So now we're looking for items that are larger than the partition element to copy them to the second part of the list. So low is pointing to that value. It is larger than that, so we swap them. So move 31 here, 71 there. Then we keep on moving high down to find if there's anything that's smaller than the partition element. So high moves past that, reaches 23. When it reaches there, it does a swap. The 23 comes here. 31 goes there. And then we then move up the low pointer. And if we find that high becomes less than low, that's when our process ends. So we're done partitioning. So after this, the list is partitioned. So we now have the first part of our list and the second part of our list. Now, we then will call the Quicksort on either parts. So, going to the next step. So, Quicksort on the first part. So we have 29, 23. You realize that, and you put the 31 right here. Realize that if we use the first thing as a partition element, the very first time we start with our high point here, we're going to do the swap, and then they'll be in place. So end up with, I'm writing the 29, but it's here already, so I can just write 23, 29 after Quicksort has been passed on this. And then for this section, we start with 73, 71, 91, 79,
53, 47, 37.
So we're going to call partition using this as a pivot element. So our high pointer stands here. And I'm just going to run through swapping when necessary. Very low. So compare that, realize that this is smaller, so I'll swap.
Temperature
73. Right. And then this is small, so it stays. So I move up my low pointer. I found something that's bigger and therefore it deserves to be in the latter part of the list. So I'm going to swap again. 73 comes here. 91 comes here. Then move down my low pointer, my high pointer. Found something that's smaller than my pivot element. Here, remember, pivot is equal to 73 here. So now, since I found something that's smaller than my pivot element, I'm going to swap there, put my 47 there, my pivot value here. Then move up my low pointer larger, should be copied over. 79 is larger. So I'm going to then swap again. Move down my high pointer again. And it seems like every step I go on this iteration, I need to swap. This is really a bad case that we've been moving towards the worst case behavior. So the 53 needs to be copied to the front part of the list, so I'll swap again. And at the end of the day, that's where the pivot element ends up. So this is now the new first part of the list for here, new second part. So we're going to call Quicksort on this part and that part again. So the parts of the list that have been broken down into smaller pieces would have, they don't need to be organized anymore. So we end up with 23, 29, 31, 37. To sort this, I'm going to be using 71 as my pivot element. So we'll go 71, that's my pivot here. Now, with the 47 and 53, if my high point starts here, I'm going to swap.
Yeah, fine. You sub to 1. You have to still stop the negative 3 and 43. Oh, sorry.
And my low pointer here would start moving up. There's nothing else that's larger than 71, the first part of the list. So low become greater than high. Now once that happens, that part of the iteration is done and my pivot element is in place. The good thing is once the pivot element gets there, then it doesn't have to move anymore, because you've just reorganized the entire list around it and it is in its place. It's in its final position once you've reorganized around the pivot element.
So you're not switching in 53 and 47?
Not yet.
High point there, no.
Not yet. So we now would have to call Quicksort again. In this case, the first part of the list would be everything in front of the pivot element. The second part of the list would be empty. That's actually a bad case for an algorithm, right? Because you're ending up doing all the aim of this algorithm is to try and split the work. But in this case, you've actually passed most of the work down to the next call. Alright, so now for here, if you choose your pivot element at the 79 in that list, you've realized that there's nothing that needs to be swapped. So, in fact, there's only one thing left in the list. So, that's good as is. Now, on the next step, that's where we try to quicksort this by choosing that as a pivot element, swapping if necessary. So go 23,
39, 31, 37.
And then 53 is our pivot with 47 as the thing to be sorted. Do the comparison, swap, and you end up with the things in order. And then you have the 71, well, my 73 should have put my pivot from here. We have 73, 79, 91. Now, while the quicksort is while we say that we can have pretty bad behavior with the quicksort because there's no guarantee that pivot element will split the list in half. In the average case, it works out pretty good. Now, there is a worst case to the quicksort, and who can guess what type of data, what organization of the data would yield the worst case behavior of the quicksort? Or reason it out?
Organized meaning whether it's descending, ascending, what?
Well, if we keep on having situations where the work, well, let's look at where the quicksort behaves well first. The quicksort will behave well if the pivot elements tend to land right in the middle of the data set, if they tend to be close to the median. If every single time we pick a pivot element though, we find out that it's right at the edge of the data and everything that it looks at is either greater than or less than it, then we really are not splitting the list in half. So we would end up with linear performance. So in the worst case, well, the order of growth for partition, the time complex of the partition procedure is theta n, because you're going to look through everything in the list and you're going to be reorganizing that list around partition element. So partition is a theta n process. If you are splitting the list in halves, then once you do your analysis, then quicksort wraps up to be a theta n log n sort. in a good case. In the average case, that normally holds. But in bad cases where the list is sorted already, once you pick the pivot element, then if this is already sorted, then everything that it's looking for will be on one side. So each successive call to Quicksort will be breaking down the list linearly. So we're going to end up with a theta in squared sort if we have a sorted list working on. And in that case, Quicksort is behaving really badly. The common term is that it's behaving pathologically. Right? And it was not that MP that started that.
Audacious.
Okay, so we're going to take a break here. When we come back, we're going to be looking at the radix sorts, and we're going to be looking at graphs also. Alright, so see you in...
So sir, I'm taking for granted that since there's